Hi everybody, I hope this video finds you well. In today's video, we're going to be finishing up section 11.9 from your textbook, which was our introduction into how to represent functions using power series. In the previous video, which was the start of 11.9, we saw how to manipulate the geometric series formula to build power series representations of different rational functions. And what we had seen thus far is sort of two main manipulations that are useful when we want to build power series representations of different functions. What we've seen thus far is that you can substitute into a power series as long as you use a polynomial with the same center. And this can lead to a change in the radius of convergence. And this has been our sort of most powerful technique so far. And it makes sense that this is our most powerful technique because we really only have one power series that we've been working with so far. We've been working with the fact that 1 over 1 minus x is equivalent to the sum from n equals 0 to infinity, x to the n. That's really been the only one that we have. So substituting into that allowed us to build power series representations for things that were similar to that rational function, but a little bit different. And substitution was our main technique for that. Do keep in mind, though, that when we substitute into a power series, this can lead to a change in the radius of convergence because not only are we going to substitute into the power series sort of formula, but we're also substituting into that radius of convergence, and that can impact the ultimate radius of convergence. The sort of second manipulation that we saw that also can be pretty useful is that you can multiply a power series by a polynomial term with the same center. This meant that if this does not change the radius of convergence, this was useful if we wanted to just multiply by like an x or an x squared or something like that, we can do that and that does not impact that radius of convergence. So far in the previous video, these were the two manipulations that we used to build power series representations of functions. We're now ready to talk about our sort of calculus manipulation of power series. These two I would sort of classify as algebraic manipulations, very useful still, and we'll continue to use them, but now we're ready to talk about a calculus manipulation that'll allow us to get even a wider range of functions represented as power series. So we've got this theorem here. This theorem says you can differentiate and integrate power series. So this is telling us first that we are allowed to differentiate and integrate power series. So that's an important piece of information. The second part of this theorem tells us that you perform these operations term by term. In other words, you can think that the derivative and the integral, which we know distribute over finite sums, also distribute over infinite sums. So when we differentiate or integrate a power series, we can move that derivative or that integral through that infinite series and just integrate or differentiate the individual terms. We should make a note here, differentiation and integration do not change the radius of convergence. So this is another manipulation sort of similar to this guy up here that's not going to impact the radius of convergence. However, as we will talk about at the very end of this video, differentiation can impact the behavior at endpoints. Differentiation can actually change convergent endpoints into divergent ones, and integration can change divergent endpoints into convergent ones. So in other words, differentiation and integration will never impact the radius of convergence, but it can impact the interval of convergence. Now, most of the time, we're not that interested, at least when we're working with power series, for the interval of convergence. We're more interested in the radius of convergence when we want to represent a function as a power series. But do want to just make a note of this, that differentiation and integration can have an impact on endpoints, but they will never impact the radius of convergence. Okay, so we now have a total of 3 different manipulations to sort of use the power series that we've already established to represent certain functions and build representations for other ones. We have substitution, multiplication by polynomial terms, and differentiation and integration. So let's see what types of functions we can now represent as power series. All right, so the first thing we're going to do is, if you think back to everything we did in the first part of 11.9, we were always representing different rational functions as a power series. Now we're going to represent a logarithmic function. So we're going to build a power series representation for f of x equals ln 1 plus x and state its radius of convergence. So how are we going to approach this? Well, keep in mind, really, we still only have that one established series, right? We have that one established series that the sum from n equals 0 to infinity xn is 1 over 1 minus x. So let's start by trying to sort of manipulate that. Let's look at 1 over 1 plus x. The reason I'm going to look at this is it should be pretty clear with our knowledge of calculus to see how this relates to this. If I go ahead and take the integral of this, this should come out as that ln 1 plus x. So let's start with trying to manipulate this. We can view this as 1 over 1 minus negative x. And we can do one of our substitutions, and we can go ahead and say, let's let z equal negative x. So we can then replace this and say that this is 1 over 1 minus z. Then at this moment, we have an established series for that. So let's go ahead and replace them. We can say that that is equal to the sum n equals 0 to infinity, z to the n. And of course, the moment you put in that series, you have to also include where this makes sense, which is on its radius of convergence, absolute value z less than 1. All right, let's go ahead and replace this now so we have an expression in terms of x. So we have the sum n equals 0 to infinity, negative x to the n, as long as negative x in absolute value is less than 1. All right, a little bit of manipulation here. We can call this the sum from n equals 0 to infinity, minus 1 to the n, so an alternating piece, and then the x to the n. And of course, in absolute value, that negative sign isn't going to matter. So that doesn't mean we get rid of the net absolute value, but we can get rid of the negative, and we can say absolute value x less than 1. So what we've just done is we built a power series representation for this rational function. 1 over 1 plus x is equivalent to this power series. So let's just summarize that real quick. So 1 over 1 plus x is equal to the sum from n equals 0 to infinity, minus 1 to the n, x to the n, as long as absolute value of x is less than 1. Okay, now again, our goal is to build a representation for this natural log. But now we have this relation to work with. So let's go ahead and integrate both sides of this. So we're going to integrate both sides with respect to x. So we'll go ahead and integrate this. We'll have a pretty messy expression on this side. And of course we need a dx there. Notice that when I do this integral here, nothing changes with the radius of convergence. That's part of the theorem we just stated. All right, over here, we know how to integrate this. If we wanted to, I guess we could say u equals 1 plus x, du equals dx, but that's not really necessary. This is just going to integrate as ln 1 plus x. Perfect, so that's what we wanted on this side. And on the right-hand side, well, part of the theorem says that this distributes over the addition, and instead you just integrate this. Now, obviously, the minus 1 to the n, that's a constant relative to x. So really, this integral is only going to apply to the x to the n. So if we apply this integral, n equals 0 to infinity, minus 1 to the n, how do we integrate x to the n? Well, the great thing about these power series is that they're infinite polynomials. And integrating polynomials is really easy. All you do is power rule. So the new exponent is n plus 1. We divide by that new exponent and have n plus 1 in the denominator. Now, at least on one of these integrals, we have to have an unknown constant. So let's put it on our right-hand side and say plus c. So there we go. Now this expression holds as long as the absolute value of x is less than 1. So notice that when we applied this integral, all we did is we took this integral through the infinite sum, which that previous theorem assured us is a legal operation. We know integrals and derivatives distribute over finite additions. Until we had that theorem, though, we didn't know they distributed over these infinite series. And it turns out they do, provided you're on the radius of convergence. So this applies through here. It's only going to impact that x to the n, because that's the only thing that is our variable that we're integrating with respect to. We used power rule, added 1 to the exponent, divided by the new exponent. Now, technically, we do need to find the value of c that makes this true, because we're looking for a specific antiderivative, not just the whole family of them. So what's the easiest thing to do here? Well, you need to plug in a value and set these things equal to each other. But you'd really rather not have to deal with this. So what you want to do is you want to evaluate both sides at the center. So let's evaluate at the center. And remember that the center here is x equals 0. So let's do x equals 0. On this side, we will get ln of 1. And on this side, because we're plugging in 0 here, we have 0 to the first power, 0 to the second power, 0 to the third, etc., etc. All that's going to be 0. So we're going to just get 0 plus c. And then we can see that that means ln of 1 has to be c, which means c equals 0. So 0 equals c. Okay, so let's summarize and rewrite this without our plus c there. So we can say that ln 1 plus x equals the sum from n equals 0 to infinity minus 1 to the n, x to the n plus 1 over n plus 1, as long as the absolute value of x is less than 1. So what we've just done there is we've built an infinite polynomial representation of a logarithmic function. When we get a little further, when we get into 11.10 in the next video, we'll actually restate this because this is one of the sort of core established theories because it's a new type of function. In the previous video, we learned how to represent rational functions using that 1 over 1 minus x representation. Now we have an established one for logarithms. ln 1 plus x equals this power series. Can we use this to get other logarithms? For sure. Right? If you want ln 1 plus 5x, well, you can just use substitution along with this series. So this is going to be an important one, and we're going to rewrite it at the start of 11.10 just to sort of summarize all our results. But for now, you should recognize that this is a big step forward from what we were doing earlier. Before we were sort of limited to just rational functions. Now we've seen how to represent a logarithm in terms of an infinite polynomial series. All right, just like we were doing in the previous one, let's briefly just take a look at a visualization of this. I'm going to take a look at a graph of this ln 1 plus x and the first couple terms of this guy here. So on this graph, you can see the blue curve is y equals ln 1 plus x. So there's the sort of blue curve there. You'll notice that because it's ln 1 plus x, it's got a vertical asymptote at -1. Here's the first 4 terms of our previous series. If you think about it, our previous series, -1 to the n, x to the n plus 1 over n plus 1, n equals 0 is going to make it positive, and then x over 1, and then n equals 1 is going to make it negative, x squared over 2, so on and so forth. The first 4 terms are right there. You'll notice that the red curve definitely doesn't look exactly the same as the blue curve, but it looks very similar to the blue curve on the radius of convergence, which is -1 to 1, these 2 black lines. So you'll notice that the red curve is a great estimator of the blue curve on the radius of convergence. And remember that this idea applies in infinitum. So this, being the first 4 terms, of course, is not expected to be exactly the same, but already, even with just 4 terms, this red curve is a very good approximation of that y equals ln 1 plus x. You might wonder why we're making such a big deal about that approximation idea. Well, the very last thing we're going to do in this chapter 11 is use these sorts of approximations to approximate values for this. If you think about it, if you needed to evaluate something like, say, ln of 2, right? Obviously, for us in the modern age, we would say, well, let's just plug in that into a calculator. But if you didn't have a calculator, or in times before calculator, how would you get a good value for ln of 2? Well, notice that if this is roughly similar to this, then ln of 2 should be roughly the same as 1 minus a half plus a third minus a fourth. Because if I plug in x equals 1 here, it should be about the same as plugging in x equals to 1 here. But notice that this is really easy because this is just fractions. This is just arithmetic. Anybody sort of with a basic knowledge of arithmetic could come up with an approximation for something as complicated as ln of 2. We'll make all of that more formal with our very last section, 11.11, but that's one of the sort of main reasons why we want to be able to build these polynomial representations. Polynomial expressions are very, very easy. Polynomials are sort of the ultimate arithmetic expression. They just involve multiplications, subtractions, additions, and exponents, which again are just multiplications. So these are very simple to work with, whereas a logarithm is a much more complicated function. Okay, so we just built a representation for a logarithm, which is very cool. Let's go ahead and see how to build a representation for an inverse trigonometric function. So we're now going to build a power series representation for f of x equals arctan of x, and we're going to state its radius of convergence. Okay, let's go ahead and take a look at how we would do that. Once again, we're not going to start by immediately going to arctan. We're going to actually look at something that's sort of related to arctan. So we're going to start with 1 over 1 plus x squared. Why am I going to start with this? Well, we know that this is directly related to arctan. If you differentiate arctan, you get this, or if you integrate this, you get arctan. So this, we can definitely go from here to here. This is also good because it's a rational expression. We know how to represent these. So we'll do our standard trick. We'll view this as 1 over 1 minus negative x squared. We'll go ahead and let z equal negative x squared. So we can do this as 1 over 1 minus z. Standard approach, rewrite that as its power series representation. N equals 0 to infinity, z to the n, as long as absolute value z is less than 1. Okay, let's go ahead and replace this back into there. So this is the sum, n equals 0 to infinity, negative x squared to the n, as long as negative x squared in absolute value is less than 1. All right, let's simplify this real quick. We'll apply this n to both things. So then we should get the sum from n equals 0 to infinity. Looks like we should get a minus 1 to the n, and then x squared to the n. Well, power to a power we multiply, so we get x to the 2n. So there's our power series representation for 1 over 1 plus x squared. Now here, obviously the negative sign doesn't matter, and square rooting 1 doesn't change anything, so the radius of convergence here is still 1. So in these last two examples, we did substitutions, but the substitutions didn't change our radius of convergence. Keep in mind, substitution may or may not change the radius of convergence. It's all based on what you substitute. In this case, our two substitutions haven't impacted the radius, but other substitutions might. Substitution is that one operation we've been talking about that could impact that radius of convergence. For now, though, we have that 1 over 1 plus x squared can be represented as this infinite polynomial. So we have 1 over 1 plus x squared is equal to the sum from n equals 0 to infinity minus 1 to the n, x to the 2n, as long as absolute value x is less than 1. All right, let's go ahead and integrate both sides. So integral 1 over 1 plus x squared dx is going to be the integral of the sum from n equals 0 to infinity minus 1 to the n, x to the 2n, again, as long as absolute value x is less than 1. So not going to impact our radius of convergence to apply that integral. On the left-hand side here, we know that that is arctan. So we get arctan x equals. Here, we know that this integral distributes over the infinite sum. So it's going to apply to this, add 1 to that exponent, 2n plus 1, and divide by that. So we get the sum from n equals 0 to infinity, minus 1 to the n, x to the 2n plus 1 over 2n plus 1. And again, that holds as long as absolute value x is less than 1. Now again, we did our integral, so we need at least 1 plus c, so I'll put the plus c here. And we'll need to figure out what that unknown constant should be. Because again, we're trying to come up with the explicit representation of arctan, not a whole family of representations. So let's go ahead and evaluate at center, which in this case is x equals 0. You always want to use the center here, because again, that's going to zero out all these terms. So we get arctan of 0 is equal to 0 plus c. Well, arctan of 0 is also 0, so we get 0 equals c. All right, so now we know that we have a representation, arctan of x is equal to the sum, n equals 0 to infinity, minus 1 to the n, or if we prefer to put all the constants in front, let's just do that way, minus 1 to the n over 2n plus 1, x to the 2n plus 1, as long as the absolute value of x is less than 1. And of course, this right here, that is our radius of convergence. Not sure if I circled it on the previous one. Let's just go back real quick and just make sure it's clear. This right here, of course, was our radius of convergence equal to 1. Okay. All right, so we now have a representation. We just did a logarithm. We'd already done rational functions. Now we've seen how to represent one of the inverse trigonometric functions in terms of an infinite polynomial. So arctan of x is equal to this sum here. Now notice that the exponent's a little more interesting here. That 2n plus 1 Well, 2n plus 1 is going to be an always odd exponent, so we're only using the odd-powered polynomials. It turns out that there's a direct relation with the fact that this has only the odd-powered exponents, and the fact that arctan of x is what we call an odd function. Remember, arctan sort of looks like this, and what we say is that this is symmetric about the origin. This reflects exactly to this. That's what it means to be an odd function, or an odd function means f of negative x is negative f of x. Well, if arctan is an odd function, then it makes sense that its polynomial representation only has odd exponents. So it turns out that that odd and even that you might have learned about it in an early algebra class, odd and even functions, directly relates to the types of powers in their polynomial representation, in their power series representation. So now we have an expression for arctan. Let's go ahead and just visually take a look at this one as well. So I'm going to show you guys a quick graph of arctan versus the first four terms of this. So once again, the blue curve, we have y equals arctan x, so there it is there. And the red curve is x minus 1/3 x cubed plus 1/5 x to the 5th minus 1/7 x to the 7th. Those are the first four terms of the series we just found. Notice they have only the odd exponents there. Notice that this one looks really good. Even just zooming in here, you can see that the red curve is really, really close to the true blue curve of arctangent on, again, -1 to 1. Obviously, huge breakdowns outside of that radius of convergence, but we're not claiming this works outside of the radius of convergence. So just on that -1 to 1, even the first four terms of this makes a great approximation in there. Notice once again, if you wanted to, say right here, if you wanted to know what is arctan of 1/2 approximately without using a calculator, well, you plug in 1/2 into there, you get 1/2 minus 1/3 1/2 cubed plus 1/5 1/2 to the 5th minus 1/7 1/2 to the 7th. Sure, that's messy, but that's all just arithmetic stuff, and you could come up with a great approximation for arctan of 1/2 just using that polynomial representation. Later on, as I mentioned, we'll get even a little more specific with that approximation, and we'll learn how large the error is when trying to use these polynomial approximations. Okay, so far already in this video, we've established two big results. We've learned how to represent logarithms and the inverse tangent function in terms of infinite polynomials. So both of the ones that we've just done here, very, very important established series. All right, let's try one other quick example because so far we've only used really integration as our main sort of manipulation. Let's at least see one example of using differentiation. All right, so I guess before we do that, let's try to make sure we can manipulate what we just had. We want to use the previous example to determine a power series representation for x squared arctan 5x and state its radius of convergence. So this is just showing you guys how to make use of the established series that we just had. So keep in mind, we just figured out that arctan of x is the sum from n equals 0 to infinity minus 1 to the n over 2n plus 1 x to the 2n plus 1 as long as absolute value x is less than 1. So this is now an established series, so anytime we see something with arctangent, we're welcome to sort of use what we've already sort of established here. So let's go ahead and take a look at how we would do this. Well, let's take a look at arctan 5x. We can go ahead and we can let z equal 5x. So we're looking at arctan of z. Why am I not worried about that x squared? Well, we know we can always multiply by x squared at the end, and then that x squared will just distribute through the power series, so we can deal with that later. So we're looking at arctan of z now. Well, we know that that is equivalent. I guess we're just going to do it as a vertical, so to say. So that is equivalent to the sum from n equals 0 to infinity minus 1 to the n over 2n plus 1, z to the 2n plus 1, as long as absolute value z is less than 1. All right, let's go ahead and replace and put that 5x back in there. So we have the sum from n equals 0 to infinity minus 1 to the n over 2n plus 1, 5x to the 2n plus 1, as long as absolute value 5x is less than 1. Can we rewrite this a little bit more nicely? Sure, we can apply the 2n plus 1 to the 5 and to the x. So we have sum n equals 0 to infinity, minus 1 to the n, 5 to the 2n plus 1 over 2n plus 1, x to the 2n plus 1, as long as absolute value of x is less than 1/5, because we can divide the 5 over. So what we've just figured out is that arctan of 5x is equivalent to this as long as we're on this radius of convergence. Now, of course, we want x squared arctan 5x, so let's go ahead and write that out. X squared arctan 5x must be equivalent to x squared times the sum from n equals 0 to infinity, minus 1 to the n, 5 to the 2n plus 1, over 2n plus 1, x to the 2n plus 1, as long as absolute value of x is less than 1/5. Notice that this, multiplying by this polynomial term, doesn't impact the radius of convergence, so we still have radius of convergence 1/5 there. Now we can distribute this x squared in. Of course, it's only going to mix with this. It's got an x squared. Since we're multiplying, we add the exponents, 2 and 2n plus 1. Well, it looks like we're going to get that x squared arctan 5x is equivalent to the sum from n equals 0 to infinity, minus 1 to the n, 5 to the 2n plus 1, over 2n plus 1, x to the 2n plus 3, as long as absolute value of x is less than 1/5. And of course, this right here tells us that the radius of convergence is 1/5. So there we go. There's our power series representation for x squared arctan 5x. We did that using a substitution and a multiplication by a polynomial with the same center 0 here, based on the established series for arctan. So now we're sort of imagining always that we have these three established series. We know, sorry about that, we have series for 1 over 1 minus x, ln 1 plus x, and arctan of x. So since we established series for all of these, you always feel welcome to use those and manipulate them directly without having to reestablish them. So if you're working with arctan, you don't need to go back through the derivation of arctangent that we just did a board or two ago. Now we can just use that we have this result, manipulate it using substitution and then polynomial multiplication. We're all good from there. All right, let's take a look at one more example now where we can actually make use of the derivative. All right. So we're going to determine a power series representation for 1 over 8 minus 2x and state its radius of convergence. This is a rational function, so this one should be pretty straightforward from what we were doing in the previous video. So 1 over 8 minus 2x. Keep in mind, we always like to have this as 1 minus something, so we need to factor out a 1 over 8. Then it looks like we should have 1 minus x over 4. Now we can let z equal x over 4. So it looks like we have 1 over 8 times 1 over 1 minus z. And now we're ready to replace that. 1 over 8, sum n equals 0 to infinity, z to the n, as long as absolute value of z is less than 1. All right, pop this guy back in there. So we get 1 over 8 summation n equals 0 to infinity. We have x over 4 to the n, absolute value z less than 1. And if we break this thing up, we can say this is 1/8 sum n equals 0 to infinity, x to the n over 4 to the n. Oh, I should pop my x back in here since we did our substitution. X over 4 in absolute value. All right, and of course here we can multiply that 4 over and get absolute value of x less than 4. All right, so anything else we can do with this? Well, sure, we can bring the 1/8 in, so let's do that and get that this is the sum from n equals 0 to infinity, 1 over 8 times 4n x to the n, as long as absolute value of x is less than 4. Now, I think I'm totally good with this format here. I would totally accept this. If you really wanted to, some people might not like the 8 times 4 to the n. It's hard to put these two pieces together, though, unless you put everything back into base 2. So if you wanted to, you could recognize the 8 as 2 cubed, and you could recognize the 4 to the n as 2 squared to the n, and otherwise 2 to the 2n, and then put these together as 2 to the 2n plus 3. Do I think that's really necessary? Not really. I would totally just accept this here, and in fact, in this case, I'll just leave it here. All right, but this right here, of course, tells us that our radius of convergence is 4. Now, something I want to talk about really briefly before we sort of finish up this example, because we're going to go ahead on the next page and use this in just a moment. But one thing I want you guys to sort of notice here is that this radius of convergence, obviously we're getting it computationally through plugging into our original radius based on our substitution and then just simplifying. But there's really sort of a meaning to this radius of convergence in a lot of our examples here. Whenever we're working with these rational functions or logarithmic functions, remember there's some discontinuities for these functions. Right? This guy has a discontinuity at x equals 4. And obviously polynomials, infinite or finite, never have discontinuities. So it should sort of make sense that the polynomials can only represent these rational functions up until that discontinuity. So if you think about it, if we're trying to build a representation that is centered at 0, right now all of our representations are centered at 0, the distance from that center, x equals 0, to that discontinuity, well, the discontinuity is at 4. The distance between 0 and 4 is 4. That's why we're getting a radius of convergence of 4. If we go back to the logarithm example, you can see the same thing. The first discontinuity in this natural log is at x equals -1, because then we get ln of 0, which we know approaches negative infinity, at least from the positive side. Well, if we're centering at 0, again, the distance between 0 and that discontinuity of -1 is our radius of convergence of 1. So there's a distinct sort of relation between this radius of convergence and the distance from your center to that first discontinuity. In fact, it's a much more sort of high-level result than we're going to be doing, but I just wanted to mention it to you guys. And keep in mind that later on, when we get into 1110 and we start to learn how to build representations that are not centered at 0, right now everything's centered at 0, but we will be able to sort of go a little further and center things wherever. That's one reason we might want to center things elsewhere. If we center it further away from a discontinuity, then that radius of convergence might widen. Okay. For now, though, let's go back to where we just left off, and we had just built a series for 1 over 8 minus 2x, and we had gotten this right here. All right, now let's use that to build a power series for a more complicated rational expression. So we want to use the previous example to determine a power series representation for this, 2x cubed over 8 minus 2x squared. You'll notice that the sort of new thing is we've seen plenty of things where we've multiplied by like 2x cubed. That's not a problem. But we've never seen anything where the denominator is entirely squared. So we've got to figure out how we're going to get that here. And again, we're going to state the radius of convergence. So we have this hint that we should start off with what we did previously. So keep in mind, we just established that 1 over 8 minus 2x is equivalent to the sum from n equals 0 to infinity, 1 over 8 times 4 to the n, which would be what we had there, yep, times x to the n, as long as the absolute value of x is less than 4. All right. Now, it might not be immediately clear, but if we just sort of use sort of the hint here to get this use the previous example, clearly integrating this isn't going to help. If you integrate this, you're probably going to get like an ln. So let's try differentiating it. So let's differentiate both sides here. So we'll differentiate both sides. And according to our theorem that we stated at the beginning, that won't have any impact on the radius of convergence. So our radius of convergence, absolute value of x, still less than 4. All right, so let's apply this derivative on both sides. Now on this side, you could certainly use quotient rule, but you could also keep in mind that this is 8 minus 2x to the -1. If we differentiate that, we should get a -1 times 8 minus 2x to the -2 times the derivative of the inside, which is -2. So that sounds like 2 over 8 minus 2x squared. Notice that's the key here, right? Is that this, by differentiating, that's how we're going to get that square in the denominator. So this derivative is 2 over 8 minus 2x squared. On this side, when we differentiate it, the other part of the theorem says that this derivative distributes over that infinite sum, and it'll go right onto this. So, of course, it's a derivative with respect to x, so this is a constant. We're just going to be differentiating this piece. So we're going to have our sum, 1 over 8 times 4 to the n, nx to the n minus 1, just using power rule. Drop the n down, subtract 1 from the exponent. Now, we need to be a little careful. In differentiation, this is something just a very minor detail, but you've got to pay attention to it. If you run this from n equals 0 still, you'd be getting x to the negative 1, which doesn't make any sense because that's non-polynomial. X to the minus 1 is 1 over x. So what happens is because you took this derivative, you lose that first term. So this actually now runs from n equals 1 to infinity. Just got to be very careful with that. Another way to think about it is that when n is 0, this thing is actually x to the 0, which means it's not actually an x, it's a constant. And when you differentiate a constant, you lose that constant and becomes 0. So now our sum runs from n equals 1 to infinity. And of course, radius of convergence, absolute value x less than 4 still. All right, if we want to, we can clean this up a little bit. We have 2 over 8 minus 2x squared. If we like to write it more with the constants all in front, we could say n over 8 times 4 to the n, x to the n minus 1, as long as absolute value of x is less than 4. Okay, this is looking a lot better. It's not quite our function, though. We wanted 2x cubed up top, but that's no problem. We just multiply both sides by x cubed. So 2x cubed over 8 minus 2x squared should be the same as x cubed times the sum from n equals 1 to infinity, n over 8 times 4 to the n, x to the n minus 1, absolute value x less than 4, because again, multiplying by a polynomial term with the same center has no impact on the radius of convergence. Now we just bring that through, we add the exponents, and we get that 2x cubed over 8 minus 2x squared is actually equivalent to the power series n equals 1 to infinity, n over 8 times 4 to the n, x to the n plus 2, as long as absolute value of x is less than 4. So in other words, this tells us radius of convergence is 4. All right, there we go. So we built a power series representation for a more complicated rational function than anything we saw in the first part of 11.9, and we did that based on the derivative. Notice the derivative acts a lot like the integral here. You just distribute it past that infinite series onto the x term, and you use power rule, which is, again, another advantage of working with these polynomial terms. They're very easy to integrate and differentiate. So there we go. All right, we're pretty much done with discussing how the derivative and integrals work with power series. We're almost ready to move into 11.10 and learn in general how to build these power series representations for any functions. At this point, we've sort of been doing it all just trying to be as clever as possible using these manipulations, the substitution, the polynomial multiplication, differentiation, integration. Turns out, though, that there is a much more sort of general approach to building power series representations of any sort of function, because at this point, we're sort of tapped out. If you try to think about how you would build something for like e to the x or sine x or cosine x, well, there's no sort of clever manipulation because no matter how many times you differentiate or integrate those, you can't make them a rational function or a natural log or an arctangent that we've already built one for. So we do need to sort of expand our approach. But before we do that, I'd like to do one last quick example to make sure that we sort of understand this idea of how differentiation and integration does not impact the radius of convergence, but could impact the interval of convergence. So we did an example sort of similar to this at the end of 11.8 to help you guys understand radius of convergence. We're going to do another one sort of about an abstract series and understanding what types of series we can conclude converge or diverge based on that information. So we're going to suppose here that we have this power series, sum a sub n x plus 1 to the n, and we have two pieces of information. We know it converges at x equals 2 and diverges at x equals negative 6. And then for each of these, we're going to decide if the series converges, diverges, or if we don't have enough or if we have not enough information. And we've got a bunch of these. Now notice that some of these, specifically these right here, where we have NaN with an n minus 1 exponent, these are all going to be based on the derivative of our original series. And these here, where we have the an over n plus 1 and n plus 1 exponent, these are all going to be based on the integral of our original series. But before we get that, let's approach this in the same way we did the last one, by sort of drawing a number line and sort of figuring out the information we have thus far. So here's a sort of number line there. Take a look at this thing. We should keep in mind that the center here, which is going to be what's really important, is x equals -1. So I'm going to put my center at x equals -1. Then I know that it converges at x equals 2. So there's 0, 1, and 2. So I know that we converge. Let's go ahead and right there. Now, of course, we know that it also must converge an equal distance the other way. So there's -2, -3, -4. Right? So it's 1, 2, 3 units that way, 1, 2, 3 units that way. So we know then that all of this stuff must converge as well on our way out to there. And same thing in the opposite direction. Now, of course, when we get to -4 itself, that's equidistant to this. This theoretically could be an endpoint, and which means that this thing, we don't know. So we'll have to go ahead and give this thing a little question mark there, because we don't know what's going to happen right at -4. Okay, let's continue on and get our other piece of information, which is that it diverges at x equals -6. So there's -5, there's -6, and we know that it diverges here. And then, of course, we know that once it starts to diverge, it's going to diverge for anything further out. And notice that that was another 1, 2 units. So we can also label here, there's 3, there's 4. Anything beyond here is also going to have to diverge. And of course, right at this value of 4 here, that's equidistant here. Maybe everything converges all the way up here, then this is a divergent endpoint. But then again, maybe this one is closed, maybe this one's open, we don't know. So that's our information there. Obviously, this little no man's land and this little no man's land, those are also going to be question marks. Okay, so first couple should be pretty normal. We have some a sub n. So this is really a sub n 1 to the n, if you think about that. And that tells us that this is really x equals 0. If we have x equals 0, then we'd have 1 to the n, an times 1 to the n. Well, that's just going to be an. X equals 0, that's solidly in the converge range. So we know that this one is going to converge. If this converges at x equals 2, then this series must also converge. This here, sum a sub n 9 to the n. What value is that in here? Well, that must be x equals 8. That's what would be giving us that 9 to the n. X equals 8, that's somewhere way down here. That's guaranteed to diverge here. Okay. Now we have this one here. We have nan 2 to the n minus 1. So the first thing we should sort of recognize here is that this is the derivative. Okay. Let's make a note of that. What is the x value that's being plugged in? Well, if we're getting a 2 there, it must be x equals 1. So x equals 1. Now notice x equals 1 puts it solidly in the convergent range. The derivative can't impact the radius of convergence, so it can't change the overall sort of distance of this. So since we're still solidly in the convergent range, well, we know that this is also going to converge. Okay. What about this one? Well, this is also the derivative here. Since we have a -5 in there, that must mean that we plugged in -6. So x equals -6. Well, what do we know about it -6? We know that it diverges. Well, if this is really, if the interval of convergence ends here and all this diverges, then of course the derivative isn't going to impact. What if this is an endpoint? Well, we said that at endpoints, the derivative can change divergent endpoints, or sorry, it can change convergent endpoints into divergent ones. But this is already divergent. So the derivative, if this is an endpoint, isn't going to change anything. And if it's not an endpoint, the derivative can't change anything. So this one will not change. So we know that this will still diverge. Okay, what about this here? Well, we have a 3 there, so that must mean that we are plugging in 2. So x equals 2. Well, x equals 2 is right here. Now, we know that it converges there, but we don't know if it's an endpoint. Now, if it isn't an endpoint, the derivative is not going to do anything. But if it is an endpoint, if it's a convergent endpoint, the derivative might, not guaranteed, but it might impact it. So since it is potentially an endpoint, and since the derivative potentially changes convergent endpoints into divergent, this actually will become a not enough information. So this will be not enough information. Again, it's a sort of very special case. It's potentially an endpoint, and potentially the derivative will affect the convergent endpoint and make it divergent. So we have to consider it as a not enough information. And again, sorry, just to make sure we fill that in, that was also the derivative. Okay, now we have some that are all based on the integral. We know that because we have that n plus 1 exponent and then divided by n plus 1. So let's take a look at as the integral here. So we have a 5 in there, which must mean that we plugged in x equals 4. So this will be x equals 4. X equals 4, well, that's right here. It's an endpoint, but it's one we already don't know about. We don't know if it converged or diverged. Since it's already something we don't know about, there's no way that the integral is going to make us know about it. This is definitely going to still be a not enough information. Okay, let's think about this guy here. This is also the integral. We have a 3 there, so that must mean that we want x equals 2. So this is going to be x equals 2. X equals 2 is potentially a convergent endpoint. If it's not an endpoint, the integral won't do anything. If it is an endpoint, the integral only potentially changes divergent endpoints convergent. So it's not going to impact this convergent one. So that means this guy is guaranteed to still converge. Again, our logic there is saying that if this isn't an endpoint, well, then the integral is not going to do anything. If it is an endpoint, it's not the type of endpoint that the integral will impact. So we know it's still going to converge. All right, last one. We again have another case of the integral here. Since we have a -5 in there, this must be x equals -6. -6 is right here. If it's not an endpoint, the integral won't do anything. But if it is an endpoint, since it's a divergent endpoint, the integral might potentially change it to convergent. So what that tells us is that this will be an example of not enough information. So once again, this example here, all of these, you should sort of go back over and make sure you understand the logic here. Really, this is supposed to just be strengthening your understanding of what does it mean for radius of convergence and how does the derivative and integral impact that. We know the derivative and integral will never impact the actual radius, but it can, in those very certain situations, potentially impact the endpoints. Differentiation can potentially change convergent endpoints into divergent ones, and integration can potentially change divergent endpoints into convergent ones. In our next video, we'll be moving into section 11.10 and taking a look at how to build power series representations for a much wider range of functions, exponential, sine, cosine, and we'll learn how to shift the center of those representations so we're not always centered at 0.